Hello students, welcome to the seventh lecture of this detection and estimation theory course. And in this particular lecture, I'm going to discuss about the Bayesian approach to simple hypothesis testing. So let me first summarize what we had done up till now. So we are given a problem at hand, which is the binary hypothesis testing problem that we have been provided. So in this we have considered two hypotheses, H0 and H1. Corresponding to these hypotheses, we have some observations, xi's, and we need to and these PDFs of these xi's are perfectly known. PDFs are known. So given this scenario, depending on the observation, we need to figure out which one of the hypotheses is correct. So this we did using the Neyman-Pearson theorem that we have discussed in the earlier classes. Now suppose that these hypotheses that we have, these occur with certain probabilities. So for example, in a communication system, let's take an example of a communication system. Let's say the hypothesis 0 tells me a 0 bit is transmitted, and hypothesis 1 tells me 1 bit is transmitted. Now we know that there could be some prior probabilities of source. What is the probability that a source is generating a bit 0 or a bit 1? Okay, so there could be some priors associated to these hypotheses. Let me call them as probability of hypothesis H0 and probability of hypothesis H1. So these are the priors that we have. All right. So this is an example of a communication system where we might know what's the probability of occurrence of these two hypotheses. And there could be many other examples where such kind of problems may arise. So in such kind of a cases, what we do is, rather than solving the optimization problem in case of a classical detection theory, that is maximize probability of detection such that the probability of false alarm is equal to alpha. Rather than solving this, what we are going to do is we are going to combine the two errors. The two errors are the probability of false alarm and probability of misdetection. We are going to combine them in certain way. Let me write to W1 and W2 as the weights and combine it to form a probability of error. Okay, so this is called as the probability of error. So I'm going to combine the two errors. The two errors are the probability of false alarm. What is the probability of false alarm? This is the probability that you detected H1 but the hypothesis H0 was true, and misdetection or a miss is the probability that you did not detect or you detected hypothesis H0 given H1 was present. So we combine these two errors, the type 1 and the type 2 errors, into some weighted form and form a composite probability of error, and then we try to minimize this probability of error in the Bayesian approach. So this is our Bayesian approach. All right, so a simple way to do this is as follows. So I can write the probability of error is equal to the probability that I detected H0 given H1 was true plus probability of I detected H1 but H0 was true. So this I can write it as probability of H0 given H1 times the probability of H1, and this one I can write it as probability of H1 given H0 times probability of H0. Now you please notice here that rather than writing probability of h0 semicolon h1, I am writing a conditional probability. This tells me that I am working on a Bayesian framework rather than a classical detection theory. Okay. So as a Bayesian, in the Bayesian approach, what our goal is to minimize this PE so that over regions R1 and R0, so that I can minimize this probability of error and maximize our detection probability. Now let us solve this problem and figure out what is going to be the Bayesian detector which minimizes this probability of error. Okay, so let me take this particular expression again and let me apply to this our optimization theory concepts. So minimize PE, which is equal to the probability of H0 given H1 times probability of H1 plus probability of H1 given H0 times probability of H0. Now what is the probability of H0 given H1? Suppose I am decide H1 if X belongs to region R1 and decide H0 if X belongs to region R0, or I can also write it to be R minus R1, okay, or R1 complement, okay. Fine. So this particular probability here is equal to the integral over region R0, probability of X given H1 is true dx and then whole times probability of H1 here, plus this probability here is integral over region R1 now because we are deciding hypothesis H1 times probability of X given H0 dx and then multiplied it by probability of H0. Okay, so this is what we want to minimize. Let me further simplify this. Let me write this particular expression as 1 minus integral over R1 probability of X given H1 hypothesis dx. Okay, so you can write this in this form. I'm changing the integral from rather than from R0, I'm integrating it over R1 times probability of H1 plus this is again the same thing, integral over R1 probability of X given H0 dx times probability of H0, and let me combine these two integrals. So this will be equal to probability of H1 plus integral over R1 probability of X minus H1 times, sorry, it should be H0 times probability of H0 minus probability of X given H1 times probability of H1 dx. So this is what I get as my PE, the probability of error. And how I can minimize this? If I will be able to minimize this if this particular quantity in the integral is less than 0 for all X belonging to the region R1. Okay, so if X belongs to region R1, I want this particular integral to be less than 0 so that my probability of error is minimized. So let's do that. So if X belongs to region R1, so this particular quantity inside the integral times probability of H0 minus probability of X given H1 times probability of H1 is less than 0. And let me simplify it further. I take this to the other side and then do a more simplification. You can see that probability of x given h1 divided by probability of x given h0 should be greater than probability of h0 divided by probability of h1. This, let me take it to be lambda. So this is going to be my answer to the problem of minimizing this probability of error. Okay, and you can see that this is a very similar kind of expression we have got from the Neyman-Pearson equation also, but in this case we know this lambda is equal to the ratio of the prior probabilities. All right, so so this is very simple case of when we are trying to minimize this probability of error. Then we get this expression, and let me simplify it further also. Let me do a cross multiplication. So I get probability of x given h1 times probability of h1 is greater than, so if this condition is true, x belongs to R1 or decide h1. If this happens, so I take this to the other side, this to the other side, and I get this particular expression here. Now you see that I can use the Bayes theorem here. I can write probability of h1 given x can be written as probability of h1 comma x, or the integral or the intersection of h1 intersection x divided by probability of x, and I can write probability of x given h1 is equal to, again the same thing, probability of h1 comma x divided by probability of h1. Now what I can do is I can take this equation, I can write it as probability of h1 comma x is equal to probability of x given h1 times probability of h1. I can put this expression here, so let me write it out here. This is equal to probability of x given h1 times probability of h1 divided by probability of x. So what I can do is I can replace this particular expression here with probability of h1 given x times probability of x. So I can write this particular expression in another form, which is probability of h1 given x times probability of x is greater than, okay, again in the right side you can do the similar thing, and we will get this particular expression times probability of x. See, probability of x is independent, it is a constant, so you can cancel out these two quantities, and what we are left with is the probability of h1 given x is greater than probability of h0 given x. We know these probabilities are called as a posterior probabilities. So the minimum probability of error leads to something called as a maximum a posteriori probability detector. What it says is that you figure out the a posteriori probabilities, probability of h1 given x, and find out the probability of h0 given x. The one which is higher, you choose that particular hypothesis. Okay, so choose h1 if probability of h1 given x is greater than probability of h0 given x. and this is called as a map detector. It is similar to our case of the Bayesian MMSE, where we figured out the estimated value to be the expectation of the a posteriori probabilities. Okay, so this is one result that we have obtained for this particular case. When we are trying to minimize the probability of error here, we get this particular expression, we solve it further to obtain a map detector. All right, now let's look at this particular expression again, or rather not this one, but let's look at this particular expression again. Let me rewrite it. Probability of x given h1 times probability of h1 is greater than probability of x given h0 times probability of h0. So if this is true, then decide h1 to be true. Okay, now let's take another case. Suppose probability of h1 is equal to probability of h2, means all hypotheses are equally likely. This may be very well true in a communication system. For example, if the probability of transmitting bit 0 is equal to probability of transmitting bit 1 is equal to half, then what will happen is that we can cancel out these two quantities here, and what we are left with is the probability. If the probability of x given h1 is greater than probability of x given h0, then we decide h1. And what are these quantities here? What do we call these quantities here? These are called as the likelihood functions. So what we are trying to do is we are trying to maximize the likelihood. So this is called as maximal likelihood detector. Okay, ML detector. So it says a very simple thing. It says that if all the hypotheses are equally likely, then you choose or you decide that hypothesis which has the maximum likelihood. All right, so in this particular lecture we have covered basically the map detector, which maximizes the a posteriori probability. The other one is the ML detector, which maximizes the maximum likelihood, which can be applied only when all the hypotheses are equally likely. All right, now there is something called as, now there is the third and the last thing. So this was the first thing that we discussed, which is called as the map detector. The second thing is called as the ML detector. All right, and this one we defined as the probability of error here. Now what we can do is, rather than defining probability of error in this fashion, I can take a very general case also. So let me take a very general case. Suppose my probability of error, so this is the third thing which I'm going to discuss, is the Bayes risk. In this, what happens is, rather than taking PE to be probability of H0 given H1 times probability of H1 plus probability of H1 given H0 times probability of H0, so these weights are predetermined depending on the prior. What we can do is, we can make this probability of error as a more general statement or a more general function in terms of the cost. So what we do is, we define a Bayes risk function let me call it to be R, which is a summation over all the hypothesis states, over all the possible outcomes. So the possible outcomes is I goes from 0 to 1, j goes from 0 to 1. Then there is some cost associated with each of these decisions times the probability that I decide hi given hj. So this is my Bayes risk function, and let me explain you better. Let me again explain you. So what is happening is that there are 4 cases. We will have 4 cases in our detection: the true and the detected. So this is h0, we detected h0. h1 is true, we detected h1. The third one is h0, we detected it to be h1. The fourth one, true, was h1, we detected is h0. This is called as the probability of detection. This one is called as the probability of false alarm, and this is the probability of misdetection. So for each of these cases we have some probabilities associated with it, and for each of these probabilities for each of these cases we can have some cost also associated with it. So for this, let me write this cost at C00. This one I'm writing as C11. This I'm writing as C. So this is my I, this is my J. So here this becomes Cij. So this is C10 and this is C01. Okay, so Cij is I can write it as the cost if we detect hi given hj is true. All right, so depending on these costs, so obviously it is intuitive that you would want these C00s and C11 to be 0. You don't want any cost associated with it, and you can have some penalties or some costs associated with these two types of errors. So what you can do is you can combine all these costs into one. So this becomes your Bayes risk function. And what our goal is to minimize the Bayes risk, which is R is equal to the two summation I goes from 0 to 1, j goes from 0 to 1, Cij times probability of hi given hj. And we can solve this problem again in a similar fashion as we did for the earlier case, and it turns out that the solution to this problem is that you detect h1 if the ratio of the likelihood functions, this is h0, is greater than C10 minus C00 times probability of h0 divided by C01 minus C11 times probability of h1, and this is equal to lambda in our case. So this is how we are going to detect using the Bayes risk function. So if we have a general weighted function for the two hypothesis scenarios, then we use the general Bayes function and then we detect using this particular expression here. Okay, let me take an example to show I will show a very specific case of the ML detector. So let me take an example here. The example is a similar example that we have taken in the earlier lectures. My hypothesis 0 is xn is equal to wn. Wn is a wide Gaussian noise with mean 0, variance sigma square. h1 is xn is given by a plus wn. N is going from 0, 1 to capital N minus 1. All right. and it is given that the priors probability of H0 and probability of H1 is both are same and is equal to half. So how we are going to detect in this case is detect H1 if the likelihood of H1 is greater than H0, or the probability of x given H1 divided by probability of x given H0 is greater than 1. So let me write these two probabilities. We have done this a lot of times earlier. So this will be 1 over 2 pi sigma square power n by 2 e power minus summation xi minus a whole square over 2 sigma square divided by 1 over 2 pi sigma square power n by 2 e power minus summation xi square over 2 sigma square is greater than 1. These two things will cancel out. This, let's take it to the numerator. It will become minus half sigma square summation xi minus a whole square minus summation xi square is greater than 1. Let me expand this particular function here. So it becomes summation xi square plus summation a square minus 2a summation xi minus summation xi square is greater than 1. You can see these two things cancelling out. Let's take the log on both the sides. So if I take log both the sides, it becomes minus 2 sigma square. Summation a square is n times a square minus 2a summation xi is greater than log of 1. Natural log of 1 will be equal to 0. So what we are going to be left with is that, so this is 0. So what we are left with is this is less than 0. This means that summation xi is 2a summation xi is greater than n times a square. A is also cancelled. Let's take this and the other side. So this is 1 over n summation xi is greater than a by 2. So this is what we get using the ML algorithm, ML detector. Why we used ML detector? Because we know that the prior probabilities are same. So we can simply use the ML detector here. And this is also intuitive also. We have seen this we see this a lot of times in our communication systems. How we detect whether a 0 or a 1 was transmitted? We take the mean of those 2 points and then we use our detector. So I end the discussion on Bayesian approach to the simple hypothesis testing problem here. In the next lecture, I'm going to take up the multiple hypothesis testing problem and show you how to solve those kind of problems. Thank you very much.